For decades, scientists sought perfection. Flawless crystalline structures, geometric patterns without defects, materials ordered with atomic precision. In the world of supercapacitors, graphene was the holy grail, carbon perfectly organized in regular hexagons like a honeycomb. If you wanted to store more energy, you needed more order, more perfection, more symmetry. Then a team from Cambridge decided to do something radical. They looked in the opposite direction. They studied chaos, disorder, the imperfections that everyone had dismissed as experimental noise. And they discovered something that shook the foundations of the field. Disordered materials store nearly twice as much energy as perfect ones. Irregularity surpasses perfection. Chaos defeats order. Welcome to Nova G, the place for ASMR. Today, we are going to explore together a discovery that could completely change the future of energy storage, and why decades of research were looking in the wrong direction. Energy storage is the great bottleneck of our civilization. Electric vehicles to renewable power grids, we all face the same dilemma. Lithium batteries take hours to charge, they degrade with every cycle, and they contain problematic materials extracted under questionable conditions. Cobalt from Congolese mines, lithium from South American salt flats that consume water in desert regions, nickel whose extraction leaves permanent environmental scars. And after 500 or 1,000 charge cycles, these batteries lose capacity irreversibly. Supercapacitors promise to solve this in a radically different way. Unlike batteries that store energy through slow chemical reactions, where lithium ions physically migrate through crystalline materials, supercapacitors do so in a purely physical and electrostatic way. When you apply voltage, the ions from the electrolyte simply migrate and align themselves on the surface of extremely porous carbon electrodes, creating two layers of charge separated by nanometric distances. There is no chemistry involved, no reactions, only pure physics. And that means extreme speed. The basic architecture is deceptively simple. Two porous carbon electrodes, an electrolyte that can be liquid or solid, and a separator. When you connect voltage, positive charges accumulate on one electrode and negative ones on the other. It is electrostatic storage pushed to the limit of what is physically possible. In China, buses already operate that, in a 30-second stop, charge enough energy to travel the next 8 kilometers. High-speed trains use supercapacitors to capture energy from regenerative braking in milliseconds, something impossible with chemical batteries. Data centers employ them as instantaneous backup against power outages. Port cranes use them to absorb energy peaks when lowering containers. Their power density is spectacular. They can absorb and release energy like a lightning bolt, thousands of times faster than any battery. But there is a devastating problem that has prevented their mass adoption for decades. Energy density is the metric that determines how much energy you can store for every kilogram of weight or liter of volume. And here, supercapacitors have lost the battle for decades. If If you wanted to replace the battery of a Tesla Model 3 with current supercapacitors, you would need a grotesquely large device that would occupy the entire interior of the vehicle and part of the trunk. Yes, it would charge in 2 minutes, but you could only drive for another 2 before running out of energy. The figures are brutal and leave no room for optimistic interpretations. A modern lithium battery, like those manufactured by Tesla or CATL, stores between 150 and 250 watt-hours per kilogram. The best current commercial supercapacitors barely reach 10 or 15 watt-hours per kilogram. It is a difference of more than 10 times, sometimes 15. To match the autonomy of a current electric vehicle of 500 kilometers, you would literally need 10 times more weight and volume in supercapacitors. It is implacable physics. For decades, scientists tried to solve this using the strategy that seemed obvious: creating materials with more and more microscopic pores. The logic was simple and visual, like thinking of a sponge. A sponge has much more internal surface area than a solid block of the same size, thanks to its millions of interconnected holes. If 1 gram of activated carbon were completely unfolded, it would have a surface area equivalent to half a tennis court. More pores meant exponentially more surface area where electrical charges could accumulate, and therefore more storage capacity. All global research focused obsessively on 2 objectives: optimizing the exact size of these nanopores so they would match the size of the electrolyte ions, and creating structures as ordered and perfect as possible at the atomic level. Graphene became the star material, carbon organized in a perfect hexagonal lattice, without defects, with uniform and predictable pores. Geometric perfection was the supreme goal. Irregularity was considered a manufacturing defect that had to be eliminated. But it turns out that this entire approach was completely wrong from the beginning. The Cambridge researchers used a technique called nuclear magnetic resonance spectroscopy, but not the medical version you know from hospitals. This is a much more sophisticated technique designed to observe how ions organize themselves at the molecular level inside nanoporous materials. They analyzed dozens of samples of carbon electrodes, each with different characteristics. They systematically varied 2 factors: the size of the pores and the degree of structural order of the material. Some were highly ordered like graphene, others completely disordered with defects and irregularities everywhere. They measured with extreme precision how much energy each sample could store, and the results were completely unexpected. First, they discovered that the size of the pores practically did not affect the storage capacity. Decades of research optimizing pore sizes had been chasing an irrelevant factor. But the second discovery was even more radical. The most disordered materials, those with irregular structures, full of defects that had historically been discarded as inefficient, stored nearly twice as much energy as perfectly ordered materials. Chaos surpassed perfection. It was completely counterintuitive. and challenged everything they thought they knew about energy storage. The explanation has to do with how ions actually interact with carbon surfaces at the atomic scale. In a perfectly ordered material like graphene, ions organize themselves in regular and predictable patterns. But that regularity also limits how many ions can accumulate on the surface. In a disordered material, the irregularities create unique microenvironments. There are corners, cracks, structural defects that allow ions to pack themselves in much denser and unexpected ways. It is like the difference between stacking perfectly square boxes versus filling a space with irregularly shaped objects. Paradoxically, sometimes irregularity allows for more efficient packing. This discovery explains why decades of attempts to create supercapacitors with increasingly perfect materials had yielded diminishing returns. They were not optimizing the correct parameter. The scientific community has described it as a fundamental turning point in the field, but translating this laboratory discovery into viable commercial devices requires solving other critical challenges. For supercapacitors to truly compete with lithium batteries, you need to optimize three factors simultaneously. First, the effective surface area of the electrode, which we now know is maximized with structural disorder. Second, the distance between charges, which ideally should be reduced to the size of a single ion. And third, the voltage window of the electrolyte. This last factor is crucial because the stored energy grows quadratically with voltage. Every additional volt that the electrolyte can withstand without degrading means an exponential increase in capacity. Conventional aqueous electrolytes decompose at around 1 volt. Organic electrolytes can reach 3 volts, but they are expensive and complicated. Current research explores revolutionary materials. Hybrid supercapacitors combine the speed of the capacitor with the capacity of a battery, using materials like tin mixed with graphene. Some prototypes already reach energy densities close to 100 watt-hours per kilogram, getting dangerously close to the territory of conventional batteries, while maintaining life cycles of up to 20,000 recharges. Beyond pure performance, there is innovation in sustainability. Scientists have created functional supercapacitors from recycled PET bottles and lignin, a byproduct of the paper industry. This means that high efficiency could go hand in hand with the circular economy. This discovery regarding structural disorder is fundamental science, not an immediate commercial product. The arduous road of engineering remains, translating this molecular knowledge into devices that also have good electrical conductivity, are economical to manufacture at industrial scale, and can survive decades of real use. But the implications are profound. If we manage to double or triple the energy density of supercapacitors by taking advantage of disordered structures, the barrier that separates them from batteries crumbles. And then everything changes. Imagine charging infrastructures where refueling your electric vehicle takes literally seconds, not hours. Perfectly stable electrical grids, thanks to massive, instant response storage that can absorb and release renewable energy on demand. Devices whose useful life is not limited by the inevitable chemical degradation of lithium batteries. Revolutionary breakthroughs rarely happen overnight. They are built upon fundamental steps like the one we are reviewing in this video. Cambridge has shown us that for decades we looked in the wrong direction, chasing perfection when we should have embraced chaos. The history of science is full of moments where our intuitions turned out to be completely wrong. We believed the Earth was the center of the universe. That time was absolute, that atoms were indivisible. Every time we challenged these certainties, the world changed. Supercapacitors teach us a deeper lesson about innovation. Sometimes progress does not come from perfecting what we already know, but from questioning fundamental assumptions. Order is not always superior to chaos. Perfection does not always defeat irregularity. And the most powerful solutions are sometimes hidden in the places we discarded as defective. The question Cambridge leaves us with is fascinating. Will we be capable of designing disorder? Will we be able to master chaos with the same precision with which we master order? If the answer is yes, the future of energy has just changed forever.